Hello students, welcome back. Previously, we went through the first type of graph problems, answering the intervals of increase and decrease, and characterizing the nature of the critical points. Local maximum, local minimum, or neither. In case of neither, the critical point is also an inflection point. How do you do that? Well, in my opinion, the best method is the diagram method. Draw a diagram kind of like this, hypothetical x-axis, and then mark the x-coordinate of the critical points, or critical numbers. X equal to -3 right here, x equal to 0 there, x equals to +3 there. These points and that point, those are not critical points. The critical points means the derivative must hit 0, and this graph is a derivative function. The derivative function, this blue graph, must hit 0, the x-axis right here, there, and finally here. -3, 0, and +3. So those are three critical numbers. 3 x-coordinates of critical points. There are 3 critical points. And then these 3 numbers divide the number line in 4 intervals. First interval, above the x-axis, this graph is a derivative function. Above the x-axis is a positive derivative value. Below the x-axis, negative derivative value. Positive again, so positive, positive. Consequently, the original function is increasing, decreasing, increasing, and increasing. So graph increases and decreases. That's where we have local maximum. Graph decreases and then goes back up. That's when we have local minimum. And then increases, pause, and increase again. That's neither maximum nor minimum. In this case, the critical point is actually an inflection point. So this diagram answers the problem perfectly. As a matter of fact, answers 2 problems, part A and part B together, completely, 100%. You don't really have to rewrite the solution like this, increasing, decreasing, increasing like this. Local minimum, local maximum, and neither maximum nor minimum, those kind of things. You don't really have to rewrite this. Now, if you write like this, and no graph, no diagram, then I'll assume these are correct answers with no justification, or at least incomplete justification. Yes, if you mark something on the graph, you're going to earn a little bit more, but still incomplete justification or no justification. If you have the diagram, then perfect. Now, even without these, even without those conclusions, if you have the diagram, that's going to be considered perfect. Because all the critical points are here, all the x-coordinates of them are here, -3, 0, 3, and the nature, max, mean, neither, they're all here. And then nature of the increasing and decreasing interval, increasing, decreasing, increasing, increasing, all those arrows, they're all here. So the diagram completes the problem. Not only the conclusion, but also the justification. Now let's go to part C and D. Oh, before going over to part C and D, let me tell you just one more about wrong solution. I see this a lot. Decreasing in -∞ to -1. Increasing in -1 to 1.5, decreasing in 1.5 to 3, and increasing in 3 to infinity. I see this a lot. If you write like this in part A, you're gonna get automatic 0 credit. What is decreasing and increasing and decreasing and increasing back again? F prime is decreasing, negative infinity to negative 1, negative 1 to positive 1, 5 increasing, and decreasing from 1.5 to 3, and increasing back again from 3 to infinity. Again, what is decreasing and increasing like this? F prime is, not the original function f. So this thing is completely wrong solution with respect to part A and part B, but still remember this. So f prime is decreasing and increasing, etc. like that. Now let's go to part C and part D. Find the intervals in which the original function is concave up and concave down. Well, here, don't look at this picture and try to answer concave up, negative infinity to negative 3, and then concave down, negative 3 to, I don't know, about negative 2, and then concave up, negative 2 to about, I don't know, about 0, and then concave down, I don't know, 0.5 to 2. That's not going to work. Remember, this is a derivative function, and the answer is about the original function. And how are they related? Like this. Let me copy and paste this thing again. Like this. And then this time, we're not really interested in this part. We're interested in this part. Concave up and down for the original function is related to the second derivative function being positive or negative, but we don't have the second derivative function here. We have the first derivative function, and first derivative function increasing and decreasing, that's related to the original function is concave up or concave down, and inflection point appears at the local maximum or local minimum of the derivative function. Derivative function here is blue, remember this? And as for the wrong solution here, f prime is decreasing, increasing, decreasing, and increasing. That corresponds to this middle column perfectly. So now, the solution here, if I move down here, it becomes a correct solution now. F prime is decreasing, increasing, decreasing, blah, 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 like that. Therefore, the original function is concave up, decreasing, so going down, concave down, and then concave up, and then decreasing, going down, and then increasing, concave up. So up is up, down is down. You see, this one here, this wrong solution now became a correct solution. So the graph going down, going up, going down, going up, that's the graph of the derivative function. So that corresponds to the concavity of the original function. Concave down, concave up, concave down, concave up. So you see, up is up, down is down. Derivative comes down, and the original is concave down. Derivative goes up, original is concave up. Derivative goes down, original is concave down. Derivative goes up finally, original is concave up. Up is up, down is down. It's easy to remember. But of course, this is okay, but they're not really the perfect solution. For perfect solution, I'd like to have a diagram similar to this. Let's see, where do we have the local extrema local minimum of the derivative function at -1, and then local maximum at 1.5, and local minimum x equals to 3, and those extrema, or the x-coordinates of those extreme points, are the inflection points of the original function. So x equal to -1, x equal to 1.5, x equal to 3, those are inflection points. And then the concavity changes. The derivative is decreasing, less than -1 decreasing, that's concave down. Derivative is increasing, that's concave up for the original function. Derivative goes down, that's concave down for the original, and derivative goes up, that's concave up for the original function. So this diagram completely answered the intervals of concavity and the x-coordinates of all inflection points. Just like the previous problem, the diagram answers everything completely along with the justification. So I highly recommend the diagram method. If you just list intervals, you will get credit for the correct answer, but probably not enough for justification. You need something else for the justification. Some markings here in the graph, but then again, markings of previous problems can be intertwined. It's really hard to see. So in my opinion, the best method is the diagram method. Okay, now sketch a possible graph of the original function. Okay, all right. So it goes kind of like this. So as we did part A and B, increasing, decreasing, increasing, pause, keep on increasing. So the sketch is like this: increasing, decreasing, increasing, and keeps on increasing like this. It's just a sketch. And then critical value x equal to 3, x equal to 0, and then x equal to 3, excuse me, this should be -3, and then I'm marking only the x coordinate. Nobody cares about the y coordinate. Now the concavity, well, right here -1, and then right here 1.5, and then 3, that's inflection point 2. So we got all those labeled, and that's a sketch. So here's a sketch, and that combines everything. In fact, here's a real graph. Increasing, decreasing, increasing, and keeps on increasing. X equal to 3, x equal to 0, x equal to -3, and also inflection point, x equal to -1, x equals 1.5, things like those. And as for the y-coordinate values, it actually shifts up and down freely, so nobody cares about the y-coordinate, to tell the truth. Anything close to this will do. Frankly, I never write sketch the graph problem in the exam, too complicated. In homeworks, of course, I can do that.